What we're doing for this exercise is solving simultaneous equations with two variables. So what we're talking about here are two equations because two variables. And what we're going to be doing is solving the point at which they intersect. So that's what it means to solve two equations. We're trying to figure out at what point that they intersect. There are three possible scenarios when we're dealing with linear simultaneous equations. So there could be one solution, there could be no solutions, or there could be infinitely many solutions, which I'm going to demonstrate using some diagrams. So we'll start off with one solution, or also known as a unique solution. As you can see here, these two simultaneous equations, these two lines, they've got different gradients, they've got a different y-intercept, and they will intersect at that one point. And so this is the whole idea, that they do not have the same gradient. They could very well have the same y-intercept, but most importantly, they do not have the same gradient, which means they are moving at different rates, which means that they are inevitably going to cross at some point. The next scenario that we have is no solution. So there is no intersection. And these lines here you may have seen before, these are the parallel lines. So because they have the same gradient, they are moving at the same rate at each point, and that means that they are never going to cross. It is important to note that they also have different y-intercepts, because if they had the same y-intercept and the same gradient, then they would be the same line. So they have the same gradient, but they do not have the same y-intercept, which is c. So our equations would be y equals mx plus c and y equals mx plus d, so different y-intercepts. The last scenario is when we have an infinite number of solutions. So in this case, the two equations have the same gradient and they have the same y-intercept. So it's increasing or decreasing at the same rate. It has the same y-intercept, as in it has the same starting point on the axes. So they are literally the same line, and whilst this may seem pretty obvious, sometimes it's not that obvious when you look at the equation itself. So as an example, 2x plus 4y is equal to 9, and negative 4x minus 8y is equal to negative 18. So this is just an example of what it might look like. Now what you'll notice is that they don't look the same. However, if we were to multiply this entire equation by negative 2, we will get the exact same equation, because 2 times negative 2 is negative 4, 4 times negative 2 is negative 8, and then 9 times negative 2 is negative 18. So what these two equations have in common is a factor. They have the exact same factor. That's an indication that it has an infinite number of solutions, because the two equations touch each other at the exact same point. So where may this come into handy, in what type of questions? Well, these are very popular types of multiple choice questions in your exam, like this one. Example 5, find the value of k for which the following simultaneous equations have a unique solutions. And unique solutions mean that they need to have different gradients. So the gradient of our first equation must not be the same as our second equation. Now we have two equations over here. Our aim is simple. We need to make sure we find a value of k, which means that the two gradients are going to be different. We can't really tell what the gradients are as it is at the moment. What we want to do is rearrange it so it is in gradient form. So we're going to call this one equation 1 and equation 2. So that's kx plus 3y is equal to 1. If I take the kx over and then divide by 3, what I'm going to get is firstly 1 minus kx, and then divide everything by 3. I'm going to get negative k on 3 as my gradient. So that's my gradient of the first line. Similarly for the second line, I've got 4x plus 3ky is equal to 0. What I want to do is get y by itself. So first thing I'm going to do is take over the 4x, and then I'm going to divide by 3k. So take the 4x over, then divide by 3k, sorry. So then what we can see is that this is the gradient. So at the moment they don't look the same, but of course depending on the value of k, they could be the same. So let's figure out what values cause these two gradients to become the same, which is what we don't want. So at what value of k are these the same? What I'm going to do at this point is I'm going to cross multiply. So take that to the top, take that to the top. So we've got negative k times 3k, so that'll be negative 3k squared. And then negative 4 times 3 is going to be negative 12. I'm then going to divide both sides by negative 3. So that will give me 4. I'm going to then take the square root of both sides, so then that's going to give me plus minus 2. So what this tells me is that when k is 2 or negative 2, the two gradients are equal to each other, which is exactly what I don't want. So what that means is I want k to not equal 2 or negative 2, because if it does, then the gradients are going to be the same. If k is not 2 or not negative 2, then we will get a unique solution. So the way that we want to write this mathematically is that k is an element of any real number as long as it's not 2 or negative 2. Rather, I should have negative 2 first, like that. So that's how we would write our answer out as an appropriate way of representing that. You can now complete these questions from 2C, 2B, and 2F.